In the realm of physics, understanding the intricacies of electric fields is paramount for comprehending the behavior of charged particles and electromagnetic phenomena. Among the many tools at our disposal, Gauss's law stands out as a beacon of elegance and practicality, providing us with a powerful lens through which we can analyze and predict the behavior of electric fields. Imagine wanting to understand the strength and direction of the wind at every point in a vast open field. It would be an incredibly tedious task to measure the wind at every single location. Similarly, determining the electric field at every point around a complex charge distribution using Coulomb's law could be quite cumbersome. This is where Gauss's law swoops in as our savior. It provides us with an elegant alternative, relating the electric field to the charge distribution in a remarkably concise manner. In the context of Class 12 physics, Gauss's law takes center stage in electrostatics, offering us a powerful tool to unravel the complexities of electric fields generated by various charge distributions. It enables us to calculate electric fields for symmetrical charge distributions with remarkable ease, bypassing the complexities of integration that would otherwise be required. As we delve deeper into the intricacies of Gauss's law, we will uncover its profound implications and learn how to wield its power to solve problems related to electric fields and their effects. So, fasten your seatbelts and get ready for an enlightening journey into the heart of electromagnetism. Before we embark on our exploration of Gauss's law, it is crucial to grasp the concept of flux. Imagine a flowing river and you place a net perpendicular to the flow. The amount of water passing through the net per unit time is analogous to flux. In the realm of electromagnetism, flux refers to the flow of electric field lines through a given surface. Electric field lines, as you know, are imaginary lines that represent the direction and strength of the electric field. The flux of the electric field through a surface is proportional to the number of field lines passing through it. If the electric field lines are perpendicular to the surface, the flux is maximum. Conversely, if the field lines are parallel to the surface, the flux is zero, as no field lines penetrate the surface. To quantify the flux, we consider a closed surface, like a balloon. A closed surface is one that encloses a volume. The flux through a closed surface is a measure of the net outflow of electric field lines from the enclosed volume. A positive flux indicates that more field lines are leaving the surface than entering it, implying the presence of a net positive charge within the enclosed volume. Conversely, a negative flux suggests that more field lines are entering than leaving, indicating a net negative charge inside. Understanding flux is fundamental to grasping the essence of Gauss's law, as the law essentially relates the flux through a closed surface to the charge enclosed within that surface. In essence, Gauss's law provides an elegant relationship between the flux of the electric field through a closed surface and the net charge enclosed within that surface. It states that the total electric flux out of a closed surface is proportional to the total charge enclosed within that surface. Imagine a closed surface, like a soap bubble, enclosing a certain amount of charge. Gauss's law tells us that the net number of electric field lines passing outward through the surface of this bubble is directly proportional to the total charge inside the bubble. This statement might seem deceptively simple, but its implications are profound. It tells us that the net charge within a closed surface dictates the electric flux through that surface, irrespective of the shape or size of the surface or the distribution of charges within it. Think of it this way. The net charge inside the closed surface acts as a source or sink of electric field lines. The more charge you have inside, the more field lines will emanate from or terminate on that charge, and consequently, the greater the flux through the enclosing surface. Now that we have grasped the conceptual essence of Gauss's law, let's delve into its mathematical representation. EDA equals sine Q underscore enclosed EO. This concise equation encapsulates the entire essence of Gauss's law. Let's break it down step by step. First, EDA. This represents the integral of the electric field, E, over the entire closed surface. The symbol denotes a closed surface integral. The dot product indicates that we are only interested in the component of the electric field perpendicular to the surface at each point. In simpler terms, this term represents the total electric flux through the closed surface. Second, Q underscore enclosed. This symbol denotes the net charge enclosed within the closed surface. And finally, EDU. This is the permittivity of free space, a fundamental constant in electromagnetism. The equation essentially states that the total electric flux through a closed surface is directly proportional to the net charge enclosed within that surface, with the constant of proportionality being 1/n. This mathematical representation of Gauss's law is a powerful tool, allowing us to calculate the electric field for various charge distributions, especially those with high degrees of symmetry. Section 5. Gauss's law and Coulomb's law, connecting the dots. You might be wondering how Gauss's law relates to Coulomb's law, which we use to calculate the force between point charges. Well, the two laws are intrinsically connected. In fact, Gauss's law can be considered a generalization of Coulomb's law. Coulomb's law tells us that the force between 2 point charges is proportional to the product of the charges, and inversely proportional to the square of the distance between them. This force is mediated by the electric field, which emanates radially outward from a point charge. Gauss's law takes a broader perspective, considering the flux of this electric field through a closed surface enclosing the charge. For a point charge, if we choose a spherical surface centered on the charge, the electric field is constant in magnitude and perpendicular to the surface at every point. Applying Gauss's law to this scenario yields the same result as Coulomb's law. In essence, Gauss's law provides a more general framework that encompasses Coulomb's law as a special case. While Coulomb's law is useful for calculating forces between point charges, Gauss's law extends our capabilities to handle more complex charge distributions and symmetrical scenarios. Section 6. Applying Gauss's law, spherical charge distributions. One of the prime applications of Gauss's law lies in determining the electric field due to symmetrical charge distributions, such as a uniformly charged sphere. Let's consider a spherical shell with a uniform charge distribution. Our goal is to find the electric field at a point outside the shell. To apply Gauss's law, we imagine a spherical Gaussian surface concentric with the charged shell, passing through the point where we want to find the field. Due to the spherical symmetry, the electric field at every point on the Gaussian surface will have the same magnitude and will be directed radially outward. Now, the flux through this Gaussian surface is simply the product of the electric field and the surface area of the sphere. According to Gauss's law, this flux is equal to the total charge enclosed within the Gaussian surface divided by epsilon naught. Since the Gaussian surface encloses the entire charged shell, the enclosed charge is simply the total charge on the shell. Plugging these values into Gauss's law equation, we can easily solve for the electric field. The beauty of this approach lies in its simplicity. We bypass the need for complex integration that would be required if we were to calculate the field using Coulomb's law. Gauss's law provides an elegant shortcut, exploiting the symmetry of the problem to our advantage. Section 7. Applying Gauss's law, infinite line charge. Let's explore another illustrative example of Gauss's law in action, an infinitely long line charge with a uniform charge density. Our mission is to determine the electric field at a point located at a certain distance from the line charge. To tackle this problem, we employ a cylindrical Gaussian surface with the line charge running along its axis. The cylindrical symmetry of the problem dictates that the electric field at every point on the curved surface of the cylinder will have the same magnitude and will be directed radially outward, perpendicular to the line charge. The flux through the curved surface of the Gaussian cylinder is then the product of the electric field and the area of the curved surface. Since the electric field is perpendicular to the end caps of the cylinder, there is no flux through these surfaces. Applying Gauss's law, we equate the flux through the Gaussian surface to the charge enclosed within the cylinder divided by epsilon naught. The charge enclosed is simply the charge density of the line charge multiplied by the length of the Gaussian cylinder. Substituting these values into Gauss's law equation, we can effortlessly determine the electric field. This example again showcases the power and elegance of Gauss's law in simplifying complex problems involving symmetrical charge distributions. By cleverly choosing appropriate Gaussian surfaces, we can circumvent tedious integration and arrive at the solution with remarkable ease. Section 8. Advantages and applications of Gauss's law. Gauss's law offers several advantages over Coulomb's law when dealing with electric fields, particularly in situations involving symmetry. First, simplicity in calculation. Gauss's law significantly simplifies the calculation of electric fields for symmetrical charge distributions, bypassing the complexities of integration often required when using Coulomb's law. Second, focus on charge distribution. It shifts our focus from individual point charges to the overall charge distribution, providing a more holistic understanding of the electric field generated by the charge distribution as a whole. Third, handling complex geometries. Gauss's law proves particularly useful when dealing with charge distributions with complex geometries, where applying Coulomb's law would be extremely cumbersome. The applications of Gauss's law extend far beyond the examples discussed earlier. Its significance is evident in various areas of physics and electrical engineering, including electrostatic shielding. Gauss's law explains why the electric field inside a hollow conductor is zero, forming the basis for electrostatic shielding. It also plays a crucial role in capacitance calculation, helping determine the capacitance of various capacitor configurations. And finally, in the realm of electromagnetic waves, Gauss's law, along with other Maxwell's equations, forms the foundation of our understanding of electromagnetic waves. Section 9. Conclusion: Gauss's law, a powerful tool in electromagnetism. In conclusion, Gauss's law stands as a cornerstone of electromagnetism, providing us with a powerful lens through which we can analyze and predict the behavior of electric fields. Its simplicity, elegance, and wide range of applications make it an indispensable tool for physicists and engineers alike. By relating the electric flux through a closed surface to the charge enclosed within, Gauss's law elegantly encapsulates the essence of electric fields generated by various charge distributions. Its ability to simplify complex calculations, particularly for symmetrical charge configurations, makes it an invaluable asset in our arsenal of problem-solving techniques. As you delve deeper into the intricacies of electromagnetism, you will find Gauss's law accompanying you every step of the way, proving its mettle time and again in unraveling the mysteries of the electromagnetic world. Embrace its power, and it will become your trusted ally in navigating the fascinating realm of charges, fields, and their intricate interactions.